Hi, my name is Nastaran Hajinazar, and I will be presenting the Virtual Block Interface, a flexible alternative to the conventional virtual memory framework. To begin, I will give a high-level summary of the talk. The motivation of this work is that modern computing systems continue to diversify with respect to system architectures, emerging memory technologies, and applications memory needs. Unfortunately, continually adapting the conventional virtual memory framework to each possible system configuration is challenging and often results in performance loss or requires non-trivial workarounds. Our goal is to design an alternative virtual memory framework that efficiently supports a wide variety of new system configurations and provides key features of the conventional virtual memory framework while eliminating its key inefficiencies. To this end, we propose Virtual Block Interface, a novel alternative virtual memory framework that delegates the physical memory management to a dedicated hardware in the memory controller. VBI efficiently adapts to different and increasingly diverse system configurations. It also reduces the overheads and complexities related to the conventional virtual memory framework. The memory controller-based memory management in VBI leads to many benefits, some not easily attainable in existing virtual memory framework, such as low overhead page walks in virtual machines and inherently virtual caches. We demonstrate the benefits of VBI with two example use cases. First, we experimentally show that VBI significantly improves performance for both native execution and virtual machine environments by 2.4 and 4.3 times respectively. Second, we show that VBI significantly improves the effectiveness of heterogeneous main memory architectures. Here's the outline for our talk today, and first let's discuss our motivation. Virtual memory is a core component of modern computing systems. The virtual memory model has remained mainly the same since it was introduced. The conventional virtual memory model was originally designed for systems whose memory hierarchy fit a simple two-level model of a small but fast main memory and a large but slow external storage. In such a configuration, the OS can easily abstract the underlying memory architecture details and present the applications with a unified view of memory. However, modern computing systems no longer follow this simple model and continue to diversify significantly. For example, with respect to emerging memory technologies and architectures, new system designs, and diverse memory requirements of modern applications. Therefore, the OS must now efficiently meet the wide range of applications' memory requirements and leverage the advantages offered by emerging memory architectures and new system designs, while simultaneously hiding their complexities from the applications. Unfortunately, this is a difficult problem to tackle in a generalized manner and results in virtual memory not being able to efficiently adapt to increasingly diverse system configurations. As a result, continuing to adapt the conventional virtual memory framework to today's diverse system configurations is challenging. Before diving into these challenges, let's take a look at the conventional virtual memory design. This figure illustrates the virtual memory management in Intel x86 as an example of a conventional virtual memory framework. In such a framework, each process is mapped to a single private virtual address space of fixed size, for example, 256 terabytes in Intel x86. The operating system controls the access permissions by managing the one-to-one mapping of processes to their associated virtual address space. The OS defines the mapping from each process's virtual address space to the physical memory and stores both the mapping information as well as permission information in a set of per-process page tables. The page tables are managed by the operating system and read by the memory management unit in the processor to perform address translation. This design suffers from many fundamental challenges when adapting to modern and diverse system configurations. Here, I describe three examples of such challenges. The first example is related to the inflexibility of the conventional virtual memory framework when adapting to the memory requirements of the modern applications. Prior works show that applications can reduce the address translation overhead using flexible page tables that are customized to the application's actual memory footprint and access pattern. For example, using larger granularities based on the density of the allocated data. However, as I mentioned earlier, in conventional virtual memory frameworks, while the OS defines the virtual to physical address mapping in the page tables, the hardware must be able to read these tables to perform address translation. This arrangement requires using rigid address translation structures that are shared between and understood by both the hardware and the OS. For example, the 4-level page tables of fixed granularity in Intel x86, and as a result, the rigidity of the conventional virtual memory framework makes it challenging to implement the page table flexibility that applications can benefit from. Another challenge exists when adapting the conventional virtual memory framework to virtualized environments. In virtualized environments, the guest OS is running on top of the host OS in a virtual machine. In such a setting, the guest OS, unaware that it is running on a virtual machine, performs memory management on the emulated physical memory and translates the guest virtual address to the guest physical address, which is in fact the host virtual address. The host then performs a second round of memory management and maps the host virtual address to the host physical address. This extra level of indirection results in many important issues, including two-dimensional page walks, where the number of memory accesses required to perform address translation increases dramatically. This issue makes it challenging to perform computation in virtualized environments efficiently. The third challenge that we discuss here arises when managing heterogeneous memory architectures. Enhancing performance with heterogeneous memories first requires dynamically mapping data to different physical memory regions according to applications' requirements. For example, mapping frequently accessed data to fast memory. And second, it needs a migration of the data when those requirements change. Since in conventional virtual memory framework, the OS defines and manages the address mapping, efficiently implementing such functionality faces the fundamental issue that the OS has low visibility into the fine-grained runtime memory behavior information. As a result, it becomes challenging to make timely migration decisions based on quickly changing memory access patterns or other dynamic behavior. Considering the key role that virtual memory has in the overall performance of the computing systems, a wide body of research proposed mechanisms to alleviate its associated overheads. However, despite notable improvements, these solutions suffer from two major shortcomings. First, they are mainly designed based on a specific system or workload characteristics, and as a result are applicable to only a limited set of problems or applications. Second, each solution requires specialized and not necessarily compatible changes to both the operating system and the hardware. Therefore, implementing these proposals at the same time in one system is a daunting prospect. This highlights the need for a holistic solution to efficiently support today's diverse system configurations. In response to the need for a holistic solution, our goal is to design an alternative virtual memory framework that has two properties. First, to efficiently and flexibly support the increasingly diverse system configurations. And second, to provide the key features of conventional virtual memory framework while eliminating its key inefficiencies. I will now describe the key idea and the guiding principles of the VBI framework. Considering the challenges that the operating system managed physical memory faces in the conventional virtual memory, the key idea in VBI is to delegate the physical memory management to dedicated hardware in the memory controller. To this end, the VBI design is driven by three key guiding principles. First, programs should be allowed to choose the size of their virtual address space. This mitigates the high translation overhead associated with unnecessarily large and fixed-size virtual address spaces in current systems. Second, address translation should be decoupled from memory protection as they are logically separate. This enables opportunities to remove address translation from the critical path of an access protection check and to defer the translation until the physical memory must be accessed, which results in lowering the overall overheads of virtual memory. It also enables the flexibility of managing address translation and access protection using separate structures customized to their characteristics. Third, software should be allowed to communicate semantic information about applications' data to the hardware. As shown by prior work, conveying data semantics to the hardware helps hardware to manage the underlying resources more intelligently. These principles address the rigidness and lack of information that is present in existing virtual memory framework and enables the reduction of its large overheads. I will now describe an overview of the VBI and how these principles are implemented. This figure shows an overview of VBI design compared to the conventional virtual memory framework. Now I will describe how VBI enables its key idea. VBI introduces a globally visible address space called VBI address space, which consists of a large set of virtual blocks of different sizes from a set of predefined size classes. All the virtual blocks are visible to all processes running on the system, and processes map each semantically meaningful unit of information, such as a data structure or a shared library code, to a separate VB of the appropriate size. The globally visible VBI address space provides VBI with system-wide unique addresses called VBI addresses. Since they are globally unique, the VBI addresses can be directly used to access all on-chip caches without requiring address translation. This enables inherently virtual caches seamlessly because there's no possibility of synonyms and homonyms since every address is unique. Accessing caches using the unique VBI addresses enables our key idea by providing VBI with the ability to defer the address translation and memory allocation until it is necessary to access the physical memory. To this end, the address translation and physical memory allocation duties are delegated to the hardware-based memory translation layer in the memory controller. This enables many benefits, such as allocation of physical memory only when the location is truly needed to write data into. It also avoids the two-dimensional page walks in virtual machines, as now the memory translation layer is the only component that performs address translation. Finally, it helps enabling flexible translation structures, as they now can be separate from the structures that maintain the access permission information. Accordingly, in VBI, the OS no longer needs to manage address translation and memory allocation. Instead, it retains full control over access protection by controlling which programs have permission to access which VBs. In order to access a VB, a process needs to be attached to that VB with correct permissions. To this end, the OS attaches the processes to the requested VBs and stores the list of the VBs attached to each process and their associated permissions in a per process table. Access protection is performed in the processor using this table to ensure that the processes has enough permission to access the requested VB. In contrast to the conventional virtual memory framework, where each process is mapped to a single fixed-size virtual address space, irrespective of its actual memory requirements, in VBI, any process can attach to any VB. Accordingly, the process's total virtual address space is defined by the set of the VBs that it actually needs and are attached to it. Therefore, the address space size of each process is defined by its actual memory needs, which satisfies our first guiding principle. Furthermore, in contrast to the conventional design, where the OS manages both the access permissions and the address mapping, VBI decouples the two by delegating the address mapping to the MTL while allowing the OS to retain full control over managing the access permissions, which addresses our second guiding principle. Decoupling address translation and access protection allows VBI to relax the constraint of sharing address translation structures with the OS, which exists in the conventional frameworks. VBI can maintain address translation information in separate structures than access permission information. This provides VBI with the flexibility to employ different types of address translation structures customized to the application's memory needs. Accordingly, VBI maintains a separate translation structure for each VB and can tune it to suit the properties of the VB, for example, single-level tables for small VBs. The flexibility of customizing the address translation structures to the VB's need lowers the address translation overhead in VBI. Each VB is associated with a set of information, including a bit vector that indicates the semantic and access properties of the VB's content, such as access pattern or latency and bandwidth sensitivity. The properties bit vector enables VBI to implement the third guiding principle by communicating the memory requirements and semantics of the data that the VB contains to the hardware. Please refer to our paper for more information, including a detailed reference implementation and microarchitecture of VBI. I will now describe the optimizations that VBI enables. VBI naturally enables a variety of important optimizations which are not easily attainable in conventional virtual memory framework. We discussed 7 examples of such optimizations in our paper, 3 of which are achieved using our guiding principle. I will explain 3 other examples of the optimizations now, and please refer to our paper to read about another example of optimizations that VBI enables. Now let's have a look at the first example optimization. A common approach to caches in the conventional framework is virtually indexed physically tagged caches. In this approach, the core issues a virtual address to the cache while the physical address is retrieved by accessing the TLB in parallel. In case of a TLB hit, the physical address is used to perform the tag lookup, and in case of a TLB miss, a page table walk is needed to retrieve the physical address that is required to read the cache. In order to remove the overheads of address translation for cache accesses, virtually indexed virtually tagged caches access the cache using virtual addresses without requiring address translation. The address translation is performed only prior to accessing the physical memory. Therefore, BIVT caches reduce the address translation overhead by reducing the number of requests for address translation. However, most modern systems do not use VIVT caches due to 2 main issues. First, since virtual addresses are not globally unique in conventional systems, VIVT caches suffer from synonyms and homonyms, which require complex mechanisms to be handled. And second, although address translation is not required to access VIVT caches, the access permission check required prior to cache access still necessitates accessing the TLB and can induce a page table walk on a TLB miss. This is due to the fact that the protection bits are stored as part of the page table's entry for each page in current systems. VBI addresses both these issues. First, it accesses all on-chip caches using VBI addresses. However, since these addresses are unique system-wide, VBI eliminates the possibility of synonyms and homonyms. Second, by decoupling address protection from address translation, VBI stores the protections and address translation information in separate sets of tables, which avoids the need to access translation structures for protection purposes. Therefore, VBI reduces the address translation overhead by naturally enabling benefits similar to virtual caches without their known complications in current systems. I will now describe the second optimization example. As I mentioned earlier, in virtually indexed physically tagged caches, the physical address is required to access the cache, which needs the data to be already mapped and allocated in the physical memory. On a cache miss, then the actual cache line is looked up and returned to the cache. In VBI, in contrast, all on-chip caches are inherently virtual and are directly accessed using the system-wide unique VBI addresses, without requiring address translation. Therefore, the physical address is not needed to access the cache, and as a result, the cache lines do not need to be mapped and allocated in the physical memory prior to being accessed in the cache. VBI exploits this opportunity and delays the allocation of physical memory for virtual blocks until it is necessary. Accordingly, on a cache miss, if MTL realizes that there is no memory allocated for the requested cache line, it simply returns a zeroed cache line. In this mechanism, the memory allocation for the VB happens when the first 30 cache line of the virtual block is written back to the memory. On the write back, the MTL defines the VBI address to physical address mapping for the virtual block and allocates the virtual block in the physical memory. The delayed physical memory allocation provides VBI with many benefits that are not easily possible in the conventional virtual memory. First, it eliminates the address translation for accesses to the regions that are not yet allocated, which reduces the address translation overhead of the system. Second, it eliminates the original memory request from accessing the memory as well by returning a zeroed cache line for accesses to the regions with no memory allocation, which results in improving the overall system performance. And finally, it avoids allocating memory for smaller VBs that may never leave the cache during their lifetime, which reduces the memory footprint of the process. As a result, by enabling delayed physical memory allocation, VBI reduces the address translation overhead, improves the overall system performance, and reduces the total memory consumption. I will now describe the third optimization example. As I mentioned earlier, the conventional virtual memory framework suffers from two-dimensional page walks in virtual machines where both the guest and the host OS perform address mapping. VBI, however, resolves this issue. In VBI, the guest and the host OS interact once to attach the process running on the virtual machine to its VB. Once attached, any memory access from the virtual machine directly uses a VBI address to access all on-chip caches. Since in VBI, the memory translation layer is the only component that manages address mapping, the address translation is performed only at the memory translation layer in the memory controller. As a result, unlike existing systems, address translation for a virtual machine under VBI is no different from that for a host. Therefore, by eliminating two-dimensional page walks, VBI reduces address translation overhead in virtualized environments. I will next discuss the methodology for testing VBI and evaluating our mechanism. For our evaluations, we use a heavily customized version of Ramlater to faithfully model all components of the memory subsystem, including TLBs and page tables. This simulator will be publicly available in July 2020. Our workloads consist of benchmarks from Spec 2006, Spec 2017, Tailbench, and Graph 500. And here is a summary of the main parameters for our simulations. I will now present our results. We evaluate VBI for two important use cases. In the first use case, we evaluate the impact of VBI on reducing the address translation overhead in both native execution and virtual machines. Here, I present results for 3 baselines and 1 VBI configuration. The baselines that we present here are native, where applications run natively on an Intel x86 system, virtual, where applications run inside a virtual machine, and perfect TLB, which is an unrealistic version of native with no address translation overhead. We also show results for VBI full, which is VBI with all 7 optimizations mentioned earlier. Please see our paper for results on more system configurations, including comparison to a recent proposal. This figure compares the performance of virtual, VBI full, and perfect TLB systems normalized to native. We make 5 observations. First, we observe that virtual reduces the performance to 0.7x on average compared to native. This is due to the two-dimensional page table walks issue in the conventional framework. Second, we observe that perfect TLB improves the performance compared to native by 1.9x on average, which is due to removing the address translation overhead completely. Third, we observe that VBI full improves the performance by 2.4x on average compared to native. This is achieved through enabling all 7 optimizations that we mentioned earlier. Fourth, we observe that VBI full improves the performance by 4.3x on average compared to virtual. This is due to the fact that in contrast to the conventional frameworks, in VBI, the address translation overhead for the processes running inside a virtual machine is no different than the processes running natively on the system. As a result, VBI enables significant performance improvements in virtual environments, which is not attainable with the conventional virtual memory framework. The fifth observation is that VBI outperforms the perfect TLB system by 49% on average. This is due to the fact that the benefits of VBI and the optimizations that it enables is not limited to only reducing the address translation overhead. The delayed physical memory allocation optimization improves the overall system performance by reducing the traffic of the program memory accesses to the main memory. Please refer to our paper for more details. We conclude that VBI can significantly improve performance in both native execution and virtual machines. As a second use case, we evaluate the benefits that VBI offers in harnessing the full potentials of heterogeneous memory architectures. To this end, we evaluate VBI in a system with a hybrid PCM DRAM main memory architecture. We examine 2 baseline systems. First, hotness unaware PCM DRAM, where the mapping mechanism is unaware of the data hotness. And second, ideal, which is an unrealistic perfect mapping mechanism that uses Oracle knowledge to always map frequently accessed data to the DRAM as the fast memory. We also evaluate a VBI configuration called VBI PCM DRAM, where VBI maps and migrates frequently accessed VBs to the DRAM. This figure compares the performance of VBI PCM DRAM and ideal normalized to hotness unaware PCM DRAM. We observe that VBI PCM DRAM improves performance by 33% on average compared to the hotness unaware PCM DRAM by accurately mapping and migrating the frequently accessed VBs to the low latency DRAM. We observe similar benefits when using VBI in a system with tiered latency DRAM, which is another heterogeneous memory architecture. Please see our paper for more details. We conclude that VBI enables efficient data mapping and migration for heterogeneous memory systems. Now let me conclude. We introduced the virtual block interface, a new virtual memory framework to address the challenges in adapting conventional virtual memory to increasingly diverse system configurations and workloads. The key idea of VBI is to delegate the physical memory management to a dedicated hardware in the memory controller. The memory controller-based memory management in VBI enables benefits not easily attainable in existing virtual memory, such as inherently virtual caches, delayed physical memory allocation, and avoiding two-dimensional page walks in virtual machines. We experimentally show that VBI significantly improves performance in both native execution and virtual machines, and increases the effectiveness of managing heterogeneous main memory architectures. We conclude that VBI is a promising new virtual memory framework that can enable several important optimizations and increase the design flexibility for virtual memory. We believe and hope that VBI will open up a new direction and many opportunities for future work in novel virtual memory frameworks. Thank you for listening to my talk. For more details, I invite you to read our ISCA 2020 paper.